Hi guys, welcome to your very first set of notes. This is our very first unit, so it's Unit 1, and it's our first set of notes in Unit 1, so we're going to call that Notes A. Usually I'll also add a little description of what the notes cover. This first set of notes goes over a lot of basic information, so even though it's not really out of a book, I'm still just going to call it Chapter 1. The first thing we should probably discuss is what are we going to study in chemistry? What is a chemistry class all about? Generally speaking, most things can be divided into two categories, matter and energy. Chemistry is the study of matter, whereas energy is something you might study more in a class like physics. We're going to focus on matter, actual particles. We're going to discuss chemical and physical changes, and then we're going to discuss things like heat flow as these changes occur. We're going to start off with a question. You may have heard of a scientific law. You may have heard of a scientific theory. So my first question for you is, what is the difference between a law and a theory? Generally, what I hear here is that a scientific law is extremely well tested. It is factual because it has been tested over and over again, whereas a theory is more in progress and not so heavily tested and therefore not so reliable. So I have another question. Do you think it is possible for a theory to become a law? Now, don't worry, those were open-ended questions and you're going to get credit for your answers regardless of what you typed there because you haven't learned the answer yet. So this is something I want you to get comfortable with in the class. When I ask you a question before I've taught you the answer, you'll get credit either way. But now I'm going to go over what the difference is, and from now on I would expect you to know the correct answer. Here are the correct definitions. A scientific law is a summary of an observed natural event. It is simply a statement of what has happened, an observation. A theory, on the other hand, is an explanation of something that occurred, a well-tested explanation of a natural event. Let me give you an example. There is both the law of gravity and the theory of gravity. The law of gravity would be what we rely on when we simply say the apple falls from the tree. The apple always goes down to the ground. We observe that. You have never seen an apple fall off of a tree and fling out into the sky. That is due to the law of gravity, an observation of a natural event. The theory of gravity, on the other hand, would describe how the center of mass of the apple and the center of mass of the earth are attracted towards each other. However, the small mass of the apple is what allows it to accelerate towards the earth, whereas the earth is bigger and therefore does not visibly accelerate towards the apple. So these both exist simultaneously. So to answer the latter question, a theory never becomes a law. A theory simply explains the law. Let's move on to another pair of words that you may have seen before. In science, we'll always be trying to see, observe, and then apply reasoning in order to make conclusions. So first we need to discuss the difference between observation and inference. What do you think the difference is? It may not be in these exact words, but I bet you said something very similar to what you see here. Observations are facts. What you see here is they use your five senses. Being able to see the apple fall, that makes it an observation. Smelling rotten eggs in a lab, great observation. An inference, on the other hand, would incorporate some already existing knowledge. It is an assumption and therefore may not be exactly correct. However, it is important to use what you know, apply your own logic when you make an inference. For example, if I saw an elephant-shaped cloud in the sky, it would be illogical to think that an elephant was actually in the sky under the cloud. We know that elephants do not typically, outside of the movies, fly around in the sky. So the elephant-shaped balloon probably does not contain an elephant. That would be applying logic. But it is possible to make assumptions that are not always correct. So it's important that you separate your observations from your inferences so you know where you have that chance of being wrong. Let's put this to the test. In a moment, I'm going to show you several sentences that are a mix of both observations and inferences. I want you to go through and select only the observations, not the inferences. Only things that you know are observations. Select those from the list. It can be a little bit tricky. A common response is that there are firefighters as an observation, but we don't necessarily know that they're firefighters. This could be a movie scene, this could be actors dressed up like firefighters. All we could really say for a fact as an observation is that there are people pictured who are dressed in firefighter outfits. There's a difference between what we know and what we can see. Or actually, I should probably say what we think we know or what we could see. Even saying there was an accident is an inference. Was there probably an accident? Yeah. But could this be a movie scene? Could this be photoshopped? Possibly. Unless you were physically there and saw the accident, that's an inference. Since we did go over the difference between observation and inference before this question was asked, your responses will be marked right or wrong. However, don't worry if you didn't get it right away. We're going to have hundreds of these questions, and one wrong answer here and there will not hurt you. Let's move on to experimental design. A good experiment will only change one variable at a time. Other variables will be controlled, and then a third variable will be measured so that we can compare the effect that one variable has on the other. So we have one thing called an independent variable and another thing called a dependent variable. Which one's which? Take your best guess based on what you remember from middle school. What is the difference between an independent and a dependent variable? Don't worry, this one won't count against you because I haven't told you the answer yet. Here's our answers. The independent variable is the thing we change on purpose. It is manipulated by the scientist. The dependent variable is the one that is measured in response to that change. It is observed and recorded by the scientist. Then we have controls. What do you think a controlled variable would be? Yep, controls are basically just that. They are controlled. They are held constant by the scientist. It is essential that only one variable is intentionally changed by the scientist and everything else is controlled. Before we move on, I want to show you a quick little memory trick to help remember which variable is which, and when we get to graphing later, which one goes on which axis. It's called dry mix. So D for the dependent variable, R because the dependent variable is the responding variable, and that'll go on the y-axis. So DRY, dependent variable responds, goes on the x-axis. Mix, M-I-X. So the M, because it's the one you manipulate, the independent variable, and then that'll go on the x-axis. So you manipulate the independent variable, put it on the x-axis. Dry mix. Since we're talking about experimental design, we of course have to talk about the scientific method, something you should know very well by now. You don't have to know these exact steps word for word. This should be a process you're very familiar with. The part I feel like gets left off a lot in the younger grades is that it's a repetitive process. So be careful when you get to the bottom here. You always want to develop new questions, share your findings, and kind of repeat the process. So let's start at the beginning. You see something weird and you ask yourself a question. Observe a phenomenon, something weird. Formulate a question. You're going to see this a lot on our lab things called a research question, maybe abbreviated RQ. So what is our research question? It needs to be something testable. Then you're going to form your hypothesis. And your hypothesis at this level should really have a basis. Maybe in grade school they let you pick whatever hypothesis that you wanted for your science fair experiment. In this class, you have to have an actual theory that supports your guess. So say, for example, you think that increasing temperature would make a reaction happen faster. You can't just guess that. You have to actually cite your source. And the theory I would use to explain that is something called collision theory that we'll learn about later, that basically says faster particles react faster. The faster movement carries more energy. Seems fairly logical, right? But you have to have that actual law or theory to back up what you're stating your guess would be in order to have a valid hypothesis at this level. Once we have developed a testable question and taken some time to research what we think is going to happen, we're going to actually conduct our experiment, and then we're going to make two different types of observations. What two types of observations have you heard of? I'll give you a hint. They both start with a Q. So the two main types are qualitative and quantitative. Qualitative focuses on the quality or descriptions, physical descriptions like color, whereas quantitative would have to do with the numbers. Usually, so many people are worried about the numbers and the calculations involved in labs that they forget to take qualitative observations. You must record qualitative observations. It could be the biggest difference in the end of deciding whether your results actually make sense or not. So never forget your qualitative observations. Of course, the numbers are important though, and the next thing that you would want to do after you've made those numerical observations, you record that data and then you're going to analyze your results. That might be in the form of calculations, perhaps a graph, something to process that data and figure out what it means, which will finally allow you to make your conclusion. And again, it doesn't stop there. Once you've made your conclusion, you may want to retest. It may bring you to new questions. You might want to share with the scientific community so that this process can develop further and further. And that's how these new experiments and new discoveries are made. It's by this repetitive process. So if you ask me, this last step, the most important part of the scientific method. Even if your lab completely fails, it could bring a new question that leads to the most successful lab that we've had in the world today. One thing that will come up when you're doing labs is that you need to make measurements. And people always ask, do we use American units? And if you could see me right now, I put that in quotation marks. It's really called the imperial system. Or are we using metric units? And more or less the answer to that is the metric units. But it's not necessarily the same exact thing as the metric system. There are some measurements that are slightly different. The SI units are something that the scientific community around the world has agreed to use. And so it's really called the international system, but it's backwards because that actually comes from the French term. It's been a while since I took French, but I'll give this a shot. The Système International des Unités. So the adjective comes after the noun, similar as in some other languages, like Spanish, for example. So that's where that comes from. We just need to know that we are using SI units, and I want to go over some basic ones that will come up from the beginning. So for length, which is the distance between 2 points, we're going to use a lowercase m, which stands for meters. You may have measured something smaller using a version of meters called a centimeter. Do you think that putting a prefix like centi in front of the word meters would still allow it to be considered an SI unit? So the question is centimeters an SI unit? The answer is yes. So would something larger, like a kilometer or kilometer. Putting a metric prefix in front of an SI unit still makes it an SI unit. It doesn't make it not an SI unit. Double negative there. So you may have different versions, but the root unit needs to be the meter. Now let's move on to volume, which is the amount of space something takes up. So volume is usually measured in liters. You may also see a smaller version, milliliters, a lot in this class. And that's going to describe your volume for your liquids and your gases, but there may be another unit used for solids, which actually kind of comes from measuring the length, and that would be centimeters, or I guess even meters cubed. If you were to take the volume, you would be doing length times width times height, 3 sides, so you get a cubed measurement. And that could be a way to represent the amount of space something that's solid is taken up. All of these things would work. And then, just so you know, a milliliter is actually equal to a cubic centimeter. So those two things are fairly interchangeable. Now let's move on to mass. So the SI unit for mass is called the gram, lowercase g, and it's going to describe the amount of matter in an object. Another version you might see a lot in this class is a kilogram, kg. This is very different than weight. The amount of mass in an object does not change, for example, if you went from the Earth to the Moon. The amount of matter would remain the same. The number of particles would remain the same, so the mass is the same. When you say your weight changes, as you might know, your weight is 1/6 of what it would be, something like that, if you went to the Moon. That is a reaction to gravity. In this class, if you remember back from the beginning, we don't actually focus on forces. That would be more of a physics thing. We study matter, so we would be using mass. We do not really want to use the word weight. It's kind of hard to get away from using weight, I understand, but it is something I'm going to try to correct you on, because you really should be talking about the amount of mass something has when you're measuring in grams. Weight should actually be measured in something called newtons if you're using the SI unit, or the imperial unit would be pounds. So really when we measure things on a scale, we're going to be looking at the mass in grams. You see when I use the word mass. Yeah, and you can use it as a noun and a verb. I'm going to mass the object, or the object's mass is 5 kilograms. Either way. The main thing I want you to try to avoid is saying that you're measuring weight in grams. Once you've made some measurements in a lab, the next thing you might want to do is compare them. And here we have two very important words that can help us give better descriptions of how our data is related to each other. So, on to a new open-ended question. What do you think the difference between precision and accuracy might be? What do you think the difference is? And here we have our answer. Now, don't worry if you didn't get that one right. That was another example of one that I asked you before. I taught you the correct answer just to see what you think. And now here we have our correct answers. Speaking of correct, let's start with accuracy. Accuracy is the term that actually means correct. You have the right answer if you have an accurate answer. Precision actually means something completely different. And a lot of people incorrectly use precision as a synonym for accuracy. Precision actually describes how close together measurements are. This definition says it's the degree of exactness in a measurement. So how can you tell if something is exact? What does that really look like if you're looking at data? So when you look at your actual numbers, more precision actually would have more decimal places. For example, 4 and 5 sound really close to each other unless I compare that to 4.4 and 4.5. The 4.4 and 4.5 are much closer together than 4.0 and 5.0, right? So the more decimals, the more we can tell how close together, how exact the numbers are. This might help you to visualize it. Let's start with this bullseye in the bottom left corner, which would represent low accuracy because they are not close to the target or bullseye in the middle, and it represents low precision as the darts are not close together. Now let's increase only precision. You can see the darts get close together. The exactness of them close together is greater, but they're still pretty far from the bullseye, so that's still representing low accuracy. Instead, let's increase only accuracy, so moving to the right but still having low precision. They're getting closer to the bullseye. They're all around the bullseye, but they're not close together. They're in 3 separate spots, so that being far apart would represent low precision, but being closer to the bullseye would represent the increased accuracy. Finally, in the top right corner, we have something that represents high accuracy and high precision. We've finally hit our bullseye, and they are all close together. So they are on target, and they are exact close together. Usually right around here I get a question about precision. If precision means being close together, then why were we talking about decimal places a minute ago? The decimal places simply help you tell how close together numbers are. Here you see the darts themselves being close together, but that could be hard to tell if you're looking at data. So increasing the number of decimal places will allow you to tell how close together the numbers are. Next, we're going to move on to some of the different types of calculations that you may need to do. The first is density. Density is essentially a ratio of mass to volume. How much matter is in a limited space? So let's compare here box A and box B. Which one do you think has a higher density? Box A has the higher density because there are more particles in a set volume. The particles are closer together. So this is easy to tell when it's visual, once you get the hang of it. Next, we want to be able to compare it quantitatively, to be able to actually calculate how dense a substance is. So let's try an example. Knowing that density is a ratio of mass to volume essentially gives us its formula. We'll use D for density equals M for mass divided by V for volume, showing that it's a mass to volume ratio, mass being on top and volume being on the bottom. So essentially, if we know two of these variables, we can solve for the third. It's a simple algebraic problem. If we're not solving for density, say we're solving for mass or volume, there's another form of being able to manipulate those variables, and that's my density triangle that I have over here. So before we actually look at the question, let me show you how to use that. You can almost see our D equals M over V formula here. D in the corner equals M divided by V. It actually works the same way if I were solving for volume. To solve for volume, I would use mass divided by density. V equals M over D. Solving for mass this way is a little bit different. When the variables are next to each other, it's multiplied. So this would read that mass is density times volume. These are the same three versions of the formula that you would get if you manipulated the original formula. The triangle is just a kind of a shortcut to help you manipulate them. Now let's read through the question and highlight our variables. What is the mass? When it says what, that means it's the unknown, so I'm solving for the mass. Of 10 milliliters. Whenever you see units like ml, you know that's one of your variables. Of a liquid that has a density of 3.76 grams per milliliter. So we've heard of grams, we've heard of milliliters. If you put them together, you can also get a unit, and you'll see where that comes from. When you use density, you put mass as grams and volume as milliliters. You could get gram over milliliter. That's all this is. So that's also a unit. It's just what we call a derived unit, or a unit that came from some other units. The next thing that I want to do is make a list of my variables. The first variable that I came across was the mass, but that was what we were solving for. That is our unknown. It says, what is the mass? The next variable that I came across was 10 milliliters. The question is, what does milliliters represent? And you should recognize the L for liters from before. What does milliliters measure? Yes, liters, and therefore milliliters measures volume. The last variable was the 3.76 grams per milliliter. So what could that grams per milliliter represent if it's not mass or volume? Of course, density. The next thing that I want to do is derive the formula in order to solve for mass. So using the triangle from before, we can use mass equals, and when the variables are next to each other, it's multiplied, D times V. Or you could just rearrange the formula that we started with. So in order to isolate M on the top, we would multiply both sides by V. And so again, you get mass equals V times D. Same exact thing. So we're going to have our mass equals our density times our volume. Now it's just plug and play. We're going to plug in the variables and solve for the answer. First, we plug in the numbers. So M equals the D, the density was 3.76 gram over ml. And yes, I want you to include your units as you work the problem. We're going to learn how these units can work just like variables by canceling out. Next, we're going to use V for volume. Plug in the 10 milliliters. So the first thing that I want to point out is with the units, since that's the new part really here. Milliliters is on the bottom of the density variable, and it is on the top, or alone, on the volume variable. When something is on the top and on the bottom, just like in regular algebra, that means it cancels. So we are going to cross that out, meaning the only variable left is the G, which is perfect because that's the unit for mass. So the mass is going to be some number of grams. Now to do the actual math. What is 3.76 times 10? Yes, 37.6. I know my handwriting can be a little bit messy, so that you can see it nice and typed out now that I've explained it. Here's this if you want to pause it. The mass is equal to the density times the volume. That was our first step to find the way to use the formula. Then we actually plugged in the density and the volume. We canceled out the milliliters, and we did the math of 3.76 times 10 to get a final answer where the mass is equal to 37.6 grams. Let's put this to the test. Let's use density to form a hypothesis, conduct an experiment, and analyze the results. We're going to look at whether Coke or Diet Coke will float in water. Which one do you think will float in water? Whichever one you guessed right there would probably not be a valid hypothesis because you probably don't have anything to base it on. Unless you happen to know a whole lot about what makes Diet Coke diet, you probably didn't have a great basis for your choice of Coke or Diet Coke. We need more information, which is why part of the scientific method is forming a valid hypothesis based on research. So let me give you some more information. First of all, the cans are the same size. And that's something you might have already known, but you didn't know exactly what the size of it is. Each can is exactly 355 milliliters. The difference is their mass. Regular Coke has a mass of 394 grams in a single can, whereas Diet Coke has 355.1 grams for one can. Now with this added information, you should be able to put together a valid hypothesis. So in a second, I'm going to ask you to try to write a sentence, a valid sentence that says, I think Coke or Diet Coke will float because, and then you have your explanation. All right, ready? What is your valid hypothesis? Before I show you what would really happen, I want you to be able to check your math. If you divide 394 grams by 355 milliliters, the density of regular Coke is 1.11 grams per milliliter. Whereas if you divide 355.1 by 355, the density of the Diet Coke is almost exactly 1. It's got 3 zeros after the decimal place before there are more digits. So it's very close to the density of water. Now let's look at what actually happens. I have a picture. You can see here that the Coke did sink to the bottom of this tank of water, whereas the Diet Coke is floating on the top. It is floating kind of hanging down into the water, which is probably because the density was just a little bit more than 1, but it's still close enough to 1 to have that buoyancy to hang out towards the top of the water. One thing you definitely should have been confident about before even looking at this picture based on those numbers is that the Diet Coke would definitely be above the regular Coke since it had less density. So why is Diet Coke less dense? Well, we know they have the same volume, so it must be the mass. Coke has 39 grams of sugar in to sweeten it, whereas Diet Coke only needs 0.1 gram of not sugar, but something called NutraSweet, that's just as sweet as Coke with way less mass. So having less mass would have a lower mass to volume ratio and therefore float or be lighter. Let's move on from density and start talking about temperature conversions. The first thing you see on your slide is the most important definition that we will probably talk about in this class. Temperature is the average kinetic energy of the system. Average kinetic energy. So kinetic energy is the energy of, well, if you didn't know, kinetic energy is the energy of motion, as opposed to maybe potential energy, which would be stored energy. Kinetic energy is about how fast the particles are moving. So if we look at that, we can kind of look at temperature. We will later learn that faster particles are higher temperature. So we have 4 main systems used to measure temperature. The Kelvin scale, notice there's not a degree sign in front of that. We have degrees Fahrenheit, degrees Celsius, which hopefully you're familiar with both of those. And then we have something called Rankine, which is used more in the Navy. The main ones that we're going to use actually are degrees Celsius and Kelvin. We'll go through a couple of units where things have to be in Kelvin, and then we'll go through another unit where things have to be in degrees Celsius. So we know we want to be able to convert from one unit to another. These are the formulas. So Kelvin is equal to degrees Celsius plus 273. To find Fahrenheit, you would take 1.8, multiply it by the temperature in degrees Celsius, and then add 32. And then to find Celsius from Fahrenheit, careful of your order operations here, you would take your degrees Fahrenheit and subtract 32, because you have your parentheses here, and then you would take that number and multiply it by 0.56. You may have seen these formulas before with 9/5 and 5/8. These are just the decimal versions of those fractions. You'll see as we move forward, we almost never use fractions. We always want our answers in decimals. Let's try an example. Let's take the human body temperature of 98 degrees Fahrenheit and convert that to Celsius and then Kelvin. So to start with, let's copy down our formula for converting to Celsius from Kelvin. Which formula is that? Although the Kelvin temperature or Kelvin conversion wouldn't have helped us much here, either of the other two would be fine. You could use the one that has Fahrenheit in front and just solve for X if you wanted to. But I'm going to go ahead and use this one where we're directly solving for degrees Celsius so we can practice this order of operations catch at the end. The next thing that I want to do is plug in the degrees Fahrenheit to where it has the degrees Fahrenheit sign in the formula. Now we want to do the 98 minus 32 before we use the 0.56, parentheses first. That gives us 66. Now we want to multiply that 66 by the 0.56 finally, or the 5/9, and that will give us our final answer of 36.96. So the temperature of the human body is 39.96 degrees Celsius, or 37 degrees Celsius. Don't worry about where to round quite yet. We're going to learn about exactly where to round very soon. Now that we have the temperature in degrees Celsius, we can solve for Kelvin. There's really not a formula to go from Fahrenheit directly to Kelvin unless you want to do a system of equations, which is totally fine with me. But I want to show, now that we've got the degrees Celsius, how to get to Kelvin. So which formula would I use for that? Correct. Kelvin equals degrees Celsius plus 273. So now I want to plug in the Celsius temperature that I got in the last step right into where it says degrees Celsius in the formula. And finally, I want to actually do the addition. What is 36.96 plus 273? And we get 309.96, so we could say the temperature of the human body is about 310 Kelvin. Again, don't worry about to round quite yet. That is coming up very soon. The last calculation we're going to go over today, and the last calculation that you'll do in your lab, is something called percent error. When we calculate the percent error, we are to determine how accurate our experimental value is. How close were we to the correct value? So the formula for this, you're going to take the accepted value, or the correct answer. You're going to find the difference from that and your experimental value. And then you're going to divide that by that accepted value. So it's accepted value minus experimental value over accepted value. You're always going to find the absolute value of that, which if you didn't know means that you just basically drop the negative sign. Absolute value means just distance from zero. So you're always going to have a positive answer for your percent error. And then of course, since it's a percent, you're going to then multiply by 100 in the end. So here we have our formula for percent error. Let's look at an example of calculating the percent error. So say we perform a lab and we want to calculate the density of gold. In the lab itself, the experiment itself, we get a value of 19.2 grams per cubic centimeters. However, the actual of density of gold, which is something you could look up, like what is the real density of gold, is 19.30 grams per cubic centimeter. So the first thing I want to do is identify my variables. I see two numbers that have units here, 19.20 grams per cubic centimeters and 19.30 grams per cubic centimeters. First question, which one is the experimental value? The experimental value would be the one done in the lab, the 19.2 grams per cubic centimeter, whereas the actual value would be the book value, the actual density. It even says actual in this problem, actually. So that's 19.3 grams per cubic centimeter. Which one of these goes in the bottom of the formula? You can go back and look at your formula. Which one of these would go in the bottom when we plug in the numbers? It's the actual value, or the correct value, that you use twice in this formula. On top, you're finding the difference between the two numbers. Then on bottom, you're putting in the actual value, in this case 19.30. You're going to find the absolute value of that, or drop the zero, and then multiply that by 100. So let's go ahead and plug everything in. Once we plug everything in, it's time to do the math. I would do the subtraction up top first and then divide that answer by our actual value. Do all of what's in the absolute value bars just as if it were in parentheses, and then multiply that number by 100. So let's give it a shot. First, subtracting the actual value from the experimental value gives you 0.1 grams per cubic centimeter. Next, dividing that number by 19.30, or the actual value, gives you 0.005 grams per cubic centimeter. But then we also have to remember to multiply by 100. And when we do that, we're going to get 0.5. That is our percent error. A common mistake is to multiply it by 100 again. You're not multiplying by 100 twice. It is actually normal. We want a very small percent error. So 0.5% error means it was a very successful lab. A high percent error, on the other hand, would represent an unsuccessful lab. And just to clarify, an unsuccessful lab does not necessarily mean that it doesn't do anything good for society. Unsuccessful simply means the hypothesis was not confirmed. There are plenty of great things that came out of unsuccessful labs. You would still write it up, and your conclusion would be that the hypothesis was not confirmed. Or the conclusion would be that the hypothesis was not confirmed. The last thing that we're going to talk about is graphing. So the first question I want to ask you about graphing is, in the past, when you've made a graph, what are some things that you always want to make sure you include on a graph? And I'm talking about formatting. What are some things that you want to do to all graphs? Here's my list. Did you have any of the same things on your list? We always want to include a title, and a title should specifically refer to the dependent and independent variables. If you label your graph graph 1 or graph of data, to me that's the same as having no title. So make sure you include your variables in the title of your graph. You should also label your x and y axis. Which one is on the x and which one is on the y? You may remember from before I taught you an acronym, DRY MIX. Look back at that and tell me, what goes on the x-axis? The x-axis should always have your independent variable, and then you plot your dependent variable on the y-axis as a function of your independent variable on the x-axis. In addition to labeling what is plotted, like temperature, for example, you should also give units, like degrees Celsius, for example. So that should be on both the x and the y-axis. Usually the units go in parentheses and are abbreviated, and the label itself is written out. You also need to make sure the scale is even spaced out for the data. And when you're doing Excel type of graphs, you want to make sure that that scale makes sense, that there's enough bars in between, and that there's not a lot of white space on the graph. That's something that we'll go over soon too. And the last thing that you actually don't always need, notice it says when appropriate, is a legend. One of my pet peeves is actually that Excel will generate a legend for you, and it just says series 1, and it's just hanging off to the side with absolutely no purpose. Delete that. When you need a legend is when you have more than one set of data presented on the same graph. And so then you would need a legend so you can tell which data set is represented with which type of line. Next, we're going to go over 3 main types of graphs. Here we have a line graph, and this is best for displaying data that changes. A very common thing to have on the x-axis here is time, displaying data that changes over time. So for example, we can look at a temperature change over time. The x-axis always has your independent variable, the y-axis would have your dependent variable. Quick side note here, notice how this plays connect the dots and the lines are connected as it moves. This is not the same as creating a graph and inserting a trend line. That's something that we're going to look at later. Next, we have a bar graph. So this is useful for comparing items side by side. When you want to show that one item is way higher than the other, you want to look at how close together different variables are. This is especially good for looking at precision, because when you can tell when 2 pieces of data are close together, the bars will be about the same height. And last but not least, we have our pie chart, which is good for displaying percentages or parts of a whole. And that completes Notes A. We did it, guys. You're done with your first set of notes. The next set of notes would be Unit 1, Notes B, Calculations.